How do we know the universe is 13.8 billion years old? This is perhaps one of the most profound questions humans have ever been able to answer. That number, 13.8 billion years, is tossed around with such confidence as if it were as simple as reading a clock on the wall. But stop and truly consider it. A billion is 1,000 million. Our entire written human history from the first Mesopotamian tablets to the smartphone in your pocket barely covers 5,000 years. The dinosaurs died out 66 million years ago. This number, 13.8 billion, dwarfs all of human experience, all of biological life on Earth, to an almost unimaginable degree. We were not there to witness the beginning. There is no cosmic birth certificate to check, no ancient text that recorded the event. So how did we, a species confined to a tiny blue dot, manage to look out into the vast dark expanse and put a date on its creation? It's important to understand first and foremost that this number is not a guess. It is not a random number, nor is it a philosophical estimate. It is a figure that has been painstakingly and meticulously constructed, piece by generations of scientists standing on each other's shoulders. It is the result of a grand investigation, a cosmic detective story that has spanned more than a century. Think of it like building a colossal pyramid. No single person could have built it. It required thousands of people, each laying a single stone, trusting that the stones laid before them were solid. One generation learned to measure the distance to the moon. The next learned to measure the distance to the planets. The next, the distance to the nearest stars. Each new discovery formed a new higher level built upon the foundation of the old ones. The 13.8 billion year answer is the final gleaming capstone on that pyramid, a testament to one of the greatest intellectual achievements of our species. It is a number derived from observation calculation and a chain of logic that is both brilliant and beautiful. The foundation of this entire structure, the blueprint for the pyramid, is a concept known as the cosmic distance ladder. This idea is more intuitive than it sounds. You cannot use a simple ruler to measure the height of a mountain, and you cannot use the same tools you use to measure a mountain to measure the distance to the moon. For every new, vaster scale, you need a new tool. The cosmic distance ladder is a series of different measurement techniques. The key is that these techniques overlap. We use the most reliable nearby method to figure out the distance to a certain object. Then we find a new method that works for that same object but also works for objects much farther away. We use the first method to calibrate the second. Then we use the second to calibrate a third, and so on. Each new method is a rung on the ladder taking us further out into the cosmos. It all starts very close to home on the first rung. We can measure the distance to planets in our own solar system with incredible precision by bouncing radar signals off them and timing the echo. We know the speed of light, so the time it takes for the ping to return tells us the distance. This gives us a rock-solid measurement of the size of Earth's orbit. We then use that orbit for the second rung parallax. This is the same principle your own two eyes use. Hold your finger out in front of your face. Close your left eye and look at your finger. Now switch closing your right eye and opening your left. Your finger appears to jump against the background. This is because your eyes are separated, giving you two different perspectives. Astronomers do the same thing, but using the largest possible separation we have Earth's entire orbit. They take a picture of a nearby star in January, and then another picture in July when Earth is on the opposite side of the Sun. The star will appear to jump slightly against the background of much more distant stars. By measuring the size of that jump, we can use simple geometry, trigonometry to calculate its distance. But parallax only works for relatively nearby stars. For things in other galaxies, they are so far away that their jump is too small to measure. We need the next rung. This is where we find one of the most important tools in astronomy, standard candles. Imagine you're in a completely dark field and you see a single light bulb. You can't tell if it's a very dim bulb that's close to you or a very bright bulb that's far away. But what if you knew it was a 100-watt bulb? If you knew its true standard brightness, you could instantly tell its distance just by measuring how dim it appears. Astronomers have desperately searched for and found these standard candles in space. The most famous are a special type of exploding star called a Type A supernova. These specific explosions are cosmic monsters briefly shining brighter than an entire galaxy. And crucially, they all explode with almost exactly the same known peak brightness. They are perfect 100-watt or rather billion watt bulbs. Here is how the ladder connects. We find these supernovae in nearby galaxies where we can also measure the distance using the previous rung, the one calibrated by parallax. This allows us to calibrate the true brightness of these explosions. Once we have that, we can look for them in the most distant faraway galaxies. We see how dim they appear, compare that to their known true brightness, and calculate how far away they are. This ladder takes us out step by step, rung by rung, to the deepest reaches of the cosmos, but this only gives us distance. How does knowing how far tell us how long ago? This is the final brilliant piece of the puzzle, and it comes in two parts. First, light does not travel instantly. It has a speed limit, the speed of light. When we look at the Sun, we are seeing it as it was 8 minutes ago. When we look at the Andromeda galaxy, our nearest galactic neighbour, we are seeing it as it was 2.5 million years ago. The light from those distant supernovae we measured has been travelling for billions of years to reach us. Looking far out in distance is literally looking back in time. The second part was the discovery of Edwin Hubble in the 1920s. Using this new distance ladder, he measured the distances to many galaxies, but he also measured their motion. He discovered something staggering: almost every galaxy in the universe is moving away from us. And even more than that, he found a direct relationship: the farther away a galaxy is, the faster it is moving away. This is the key. The universe is expanding. It's not that we are the centre, it's that the entire fabric of space itself is stretching like a loaf of raisin bread rising in the oven. As the bread space expands, every raisin galaxy moves away from every other raisin. If the universe is expanding today, it must have been smaller yesterday, and smaller the day before that. We can use the distance ladder to measure how far the galaxies are, and we can use their light to measure how fast they are moving apart. This is called redshift. With those two pieces of information, distance and speed, we can run the cosmic movie in reverse. We can calculate if galaxy X is this far away and moving at this speed. How long did it take to get there? We can do this again and again for all the galaxies we can see. And when we rewind the clock, all of them in every direction appear to have started from the same single incredibly dense point. That calculation, the time it would take for an expanding universe to get to its current size, is what gives us the age. That is the 13.8 billion year journey. It is the time it has taken for the cosmos to expand from a hot, dense beginning to the vast star-filled universe we see today. It is not a guess. It is a measurement built on a ladder of logic and observation that reaches from our own backyard to the very edge of time itself. To measure the universe, we must start with our own neighbourhood. The first and most fundamental rung on our cosmic distance ladder is called parallax. This method is based on simple geometry, and it's something you use every single day without thinking about it. Hold your thumb out at arm's length, close your left eye and look at your thumb against the distant background like a wall or a tree. Now switch eyes. Close your right eye and open your left. Your thumb will appear to jump or shift its position against that background. This shift is parallax. You are using the distance between your two eyes, your baseline, to see this shift. Your brain instinctively uses this tiny jump to judge how far away your thumb is. If you bring your thumb closer to your face and repeat the experiment, the jump will be much larger. A bigger jump means the object is closer. A smaller jump means it's farther away. To measure a star, we need a much bigger baseline than the distance between our eyes. Luckily, we have the orbit of the Earth around the Sun. Here is how astronomers use it. In January, we use a powerful telescope to take a picture of a nearby star. We carefully note its position against the background of much more distant stars. Those background stars are so incredibly far away that they appear completely fixed like the distant wall behind your thumb. Then we wait 6 months. By July, the Earth has travelled to the other side of the Sun. We are now at a different point in our orbit, about 300 million kilometres or 186 million miles from where we were in January. We take a second picture of that very same star. Just like your thumb, that nearby star will appear to have shifted its position against the fixed, distant background. This tiny shift is its parallax angle. By measuring this angle and knowing the size of our baseline, the diameter of Earth's orbit, we can use basic trigonometry to calculate a direct physical distance to the star. This is the gold standard of distance measurement. It's pure, reliable geometry. For decades, however, this was incredibly difficult. The parallax shifts of stars are minuscule. Measuring them from the ground through our planet's blurry, turbulent atmosphere was a massive challenge. We could only get reliable parallax distances for a few thousand stars all in our immediate cosmic vicinity. The foundation of our ladder was small and a bit shaky. This all changed with the launch of the European Space Agency's Gaia satellite. Gaia is a space observatory whose entire mission is to measure parallax. Floating above Earth's distorting atmosphere, Gaia is a revolutionary precision instrument. It can measure angles with an accuracy of micro-arcseconds. It's difficult to overstate how small a micro-arcsecond is. An arcsecond is 1/3600th of a degree. A micro-arcsecond is 1/1,000,000th of that. It is the same as measuring the width of a single human hair from over 600 miles 1,000 kilometers away. With this astonishing power, Gaia is not just measuring thousands of stars, it is mapping billions of them. It has created a breathtakingly precise three-dimensional map of our section of the Milky Way. Gaia has single-handedly taken the first most important rung of the distance ladder and made it solid, broad, and incredibly deep. It provides the rock-solid foundation upon which all other measurements must be built. Rung 2 standard candles, the Cepheid variables. Parallax is powerful, but it has a limit. Even Gaia cannot measure the tiny angular shifts of stars in other galaxies. They are simply too far away. Their jump is too small to detect. To measure the distance to our galactic neighbours, we need a new tool. We need a standard candle. What is a standard candle? Imagine you are on a completely dark road at night. You see a single light in the distance. How far away is it? It's impossible to tell. It could be a very bright light, like a car's headlight that is very far away. Or it could be a very dim light, like a small flashlight that is very close. You can't know the distance because you don't know the light's true brightness, its intrinsic luminosity. But what if you had a special rule? What if you knew somehow that every single car headlight in the world was manufactured to be exactly the same brightness? Now you could tell the distance. If the headlight looked very bright, it must be close. If it looked very dim, it must be far away. Because you know its true brightness, you can calculate its distance just by measuring its apparent brightness, how bright it looks to you. This light of known brightness is a standard candle. Astronomers needed to find a standard candle in the cosmos. They found it in a special type of star called a Cepheid variable. Cepheids are very large, very bright stars that are unstable. They don't shine with a steady light. Instead, they pulsate, growing brighter, then dimmer, then brighter again in a perfect, reliable rhythm. In the early 1900s, an astronomer named Henrietta Leavitt was studying these stars. She made a discovery that would change astronomy forever. She found a direct, unbreakable link between a Cepheid's pulsation period, how long it takes to go from bright to dim and back, and its true brightness. She found that the brightest, most powerful Cepheids took a long time to pulse, perhaps 50 or 60 days. The dimmer Cepheids pulsed very quickly, perhaps only 1 or 2 days. This was the key. Now an astronomer can look at a distant galaxy and find a Cepheid star. They don't need to know the distance. They just need to watch the star and time its pulse. The astronomer says this Cepheid takes 30 days to complete its cycle. They can then look at Henrietta Leavitt's chart, now called the period luminosity relation, and find out the star's true brightness. Okay, a 30-day period means its true brightness is X. Next, they measure the star's apparent brightness from their telescope. They compare the true brightness X to the apparent brightness they see. The difference tells them the distance. This tool is the second rung of our ladder. It was famously used by Edwin Hubble in the 1920s. He pointed his telescope at the fuzzy Andromeda Nebula, which most people thought was a cloud of gas inside our own Milky Way. He found Cepheid stars in it. He measured their periods, calculated their true brightness, and determined their distance. His calculations showed that Andromeda was millions of light years away, far, far outside the bounds of our own galaxy. He had proven that our universe was not just one galaxy, but was filled with countless island universes, just like our own. How do we calibrate this rung? How do we know the exact brightness for a 30-day Cepheid? We do it by finding Cepheids in our own galaxy that are close enough to have their distance measured with rung 1 parallax. Gaia has now provided ultra-precise distances to many nearby Cepheids, allowing us to lock rung 2 onto rung 1 with incredible accuracy. Rung 3. Supernova, the standard bombs. Cepheids are brilliant. They allowed us to measure the distances to nearby galaxies and prove the universe is vast. But they have a limit. In galaxies that are too far away, hundreds of millions or billions of light years, we can no longer pick out individual Cepheid stars. They are too faint and blur into the general glow of their host galaxy. To measure the true deep expanse of the cosmos, we need a standard candle that is billions of times brighter. We need a standard bomb. We found it in a special kind of explosion called a Type Ia supernova, pronounced Type 1a. This is not just any star exploding. A Type Ia supernova happens in a very specific situation. It starts with a binary star system, 2 stars orbiting each other. One of these stars has already lived its life and died, becoming a white dwarf. A white dwarf is the super dense, burnt-out core of a star like our Sun crushed by gravity, until it is only the size of the Earth. This tiny dense white dwarf is so heavy that its powerful gravity starts to pull material like hydrogen and helium gas off of its healthy companion star. This stolen gas streams onto the white dwarf, piling up on its surface like snow on a mountaintop. The white dwarf gets heavier and heavier, but there is a fundamental law of physics, a magic number in the universe known as the Chandrasekhar limit. This limit, discovered by the physicist Subrahmanyan Chandrasekhar, states that a white dwarf cannot be heavier than about 1.4 times the mass of our Sun. As the white dwarf steals material from its partner, its mass creeps closer and closer to this 1.4 solar mass limit. When it hits that exact mass, the pressure and temperature in its core becomes so great that it triggers a runaway thermonuclear explosion. The entire white dwarf detonates in a fraction of a second. This is what makes it a standard candle, because every Type Ia supernova is triggered by the exact same process. A white dwarf at the exact same mass, the Chandrasekhar limit, the resulting explosion is remarkably consistent. They all reach the same peak true brightness, and that brightness is almost unimaginable. For a few weeks, a single Type Ia supernova can outshine its entire host galaxy of hundreds of billions of stars. They are so bright that we can see them clear across the visible universe. When astronomers spot one of these explosions in a galaxy billions of light years away, they know its true brightness. They measure its apparent brightness, and the comparison gives them the distance. This is the third and highest rung on our ladder. To calibrate this rung, we must find a galaxy that is close enough for us to see both Cepheids stars and a Type Ia supernova. We use the Cepheids rung 2 to find the distance to that galaxy. Then we use that known distance to calculate the true brightness of the supernova. This locks rung 3 onto rung 2. These Type Ia supernovae are the cosmic lighthouses that allowed astronomers to map the most distant reaches of the universe. And in doing so, they led to the shocking discovery that the expansion of the universe is not slowing down, but speeding up a mystery attributed to dark energy. Challenges and refinements. Keeping the ladder straight. This ladder system, parallax calibrating Cepheids, which calibrate supernovae, is beautiful, but the universe is a messy place. Several challenges can wobble the rungs and throw off our measurements. The first major challenge is cosmic dust. Space is not perfectly empty. It is filled with tiny microscopic grains of dust and gas. Imagine our standard candle is a lighthouse on the coast. We know its true brightness, so we can calculate its distance based on how bright it looks. But what if it's a foggy night? The fog will block some of the light, making the lighthouse appear dimmer. If we don't account for the fog, we will incorrectly think the lighthouse is much farther away than it truly is. Cosmic dust does the same thing. It dims and reddens the light from distant stars and supernovae. Astronomers must be incredibly careful to measure this cosmic fog, a process called measuring extinction, and correct for it or all their distances will be wrong. A second more subtle challenge is metallicity. In astronomy, metals are any elements that are not hydrogen or helium. A star with high metallicity is rich in elements like carbon and iron. A star with low metallicity is almost pure hydrogen and helium. The problem is that a Cepheid star's chemical makeup, its metallicity, might slightly change how it pulses. A metal-rich Cepheid might have a slightly different period-luminosity relationship than a metal-poor one. This would be like discovering that our standard 100-watt bulbs are not all the same. The ones with a slightly different filament, different metallicity, are actually only 95 watts. This would introduce a small but systematic error that could corrupt the entire ladder. Because of these challenges, astronomers desperately wanted an independent way to check their work. They needed a cosmic Rosetta Stone, a way to measure a distance to a faraway galaxy that did not rely on Cepheids or parallax at all. They found it in a galaxy called NGC 4258. This galaxy is special. At its very center, a supermassive black hole is orbited by massive clouds of water molecules. These water clouds are so energized that they act like natural masers, which are like lasers, but they emit microwave radio waves instead of visible light. Using a global network of radio telescopes, astronomers could track these water masers as they orbited the black hole. They could measure their orbital speed in kilometers per second using the Doppler shift, and they could also track their tiny physical movement across the sky, their angular motion. By combining their physical speed with their angular speed, astronomers could use pure geometry to calculate a direct ironclad distance to the galaxy. This method completely bypassed the entire parallax Cepheid ladder. It was a brand new independent anchor point. When they calculated the distance to NGC 4258, about 23 million light years, they could then find the Cepheid stars in that same galaxy and check their calibration. This Rosetta Stone measurement powerfully confirmed and refined our understanding of the ladder, giving us immense confidence in our measurements. Conclusion: the cosmic scaffold. We have built our way up from our backyard to the edge of the cosmos. Rung 1. Parallax used geometry to map our local stars. Rung 2 Cepheids used standard candles to map nearby galaxies. Rung 3 supernovae used standard bombs to map the universe itself. For a long time, this was called the distance ladder, because each step depended on the one before it. This was also a source of great anxiety. If the first rung was weak, the entire ladder above it would be unstable. But today, ladder is no longer the best word. A better word is a scaffold. A scaffold like one used to build a skyscraper is not a single linear path. It is a robust interconnected web of supports. It has multiple vertical beams and multiple horizontal cross braces. If one joint is a little loose, the rest of the structure holds it firmly in place. This is modern cosmology. We have many new independent methods for measuring distance. The prompt mentioned TRGB tip of the red giant branch, which is another type of standard candle that uses the predictable brightness of old dying stars. This TRGB method can be used to check the Cepheid method. The Watermasser method from NGC 4258 can be used to check them both. We have multiple ways to calibrate our supernovae. Each method checks and reinforces the others. This powerful overlapping and cross-checked cosmic scaffold is what gives astronomers such certainty. It is this robust structure that has allowed us to confidently map the universe in 3 dimensions, to trace the history of cosmic expansion, and to uncover the profound and dominant mysteries of dark matter and dark energy, which will be the subject of our next discussion. Imagine the universe is not a giant empty box with galaxies flying through it like thrown baseballs. Instead, imagine the universe is a vast, flexible canvas. The galaxies are not flying across the canvas, they are like dots painted onto it. Now imagine someone is stretching that canvas in all directions. The dots themselves are not moving, but the space between them is growing. This is the core concept of our modern understanding of the universe. Space itself is expanding. But how could we possibly know this? We can't see the edge of the canvas being pulled. We measure it using a fantastic tool called redshift. To understand redshift, think about sound. When an ambulance passes you, it soon sounds high-pitched as it comes toward you and then suddenly drops to a low pitch as it moves away. This is the Doppler effect. The sound waves are squished as it approaches and stretched as it recedes. Light behaves in a similar way. Light travels in waves. Blue and violet light have short squished waves. Red and orange light have long stretched waves. If an object like a star or a galaxy is moving away from us at high speed, the light waves it emits get stretched out on their journey to us. As light shifts toward the red end of the spectrum, we call this redshift. A tiny bit of redshift might mean an object is just moving away from us inside our own galaxy. But when we look at distant galaxies, we see something much more profound. It's not just a regular Doppler shift. The light waves are being stretched because the very fabric of space they are traveling through is expanding. As a photon of light travels for billions of years across the cosmos, the universe itself stretches, and that wave of light stretches right along with it. The longer it travels, the more it gets stretched, and the redder it appears when it finally reaches our telescopes. This is where the great discovery of Edwin Hubble and Georges Lemaitre comes in. In the 1920s, they measured the redshifts of many different galaxies. They also measured their distances. When they plotted their data, a stunning pattern emerged. The farther away a galaxy is, the more its light is redshifted. This relationship, now called the Hubble-Lemaitre law, was the first hard proof that the universe is expanding. It means the farther a galaxy is from us, the faster it appears to be moving away. This is exactly what you would expect to see if the canvas of space was stretching. A dot 1 inch away from you might move 1 inch farther in a second, but a dot 10 inches away would move 10 inches farther in that same second because there is more canvas to stretch between you and it. For decades, this was the accepted story. The universe began with a big bang and has been expanding ever since, but there was a big question everyone wanted to answer. What is the fate of the universe? Logically, the expansion should be slowing down. The universe is full of stuff, galaxies, gas dust, and mysterious dark matter. All of this stuff has gravity. Gravity is a force that pulls, not pushes. Just like a ball thrown into the air is slowed down by Earth's gravity. The combined gravity of all the matter in the universe should be pulling back on the expansion, acting like a cosmic brake. Scientists spent decades trying to measure exactly how much it was slowing down. Then in 1998, 2 teams of astronomers made a discovery that shocked the entire world. They were using a special type of exploding star called a type Ia supernova to measure vast distances. These supernovae are like standard candles because they all explode with almost the exact same brightness. By seeing how dim they appear, astronomers can calculate precisely how far away they are. When they looked at these incredibly distant supernovae, they found something impossible. They were dimmer than expected. This meant they were farther away than the slowing down model predicted. The only way this could be true is if the expansion of the universe was not slowing down at all. In fact, it was speeding up. This was like throwing a ball into the air and watching it suddenly shoot upward faster and faster as if an invisible rocket engine had ignited. Gravity, the force we thought ruled the cosmos, was losing. This discovery forced scientists to propose a new mysterious force. If gravity is pulling the universe together, there must be something else, something more powerful that is pushing it apart. They gave this something a name: dark energy. We have no idea what dark energy is. It is not matter. It is not light. It seems to be a property of empty space itself. It acts like an anti-gravity pressure inherent in the vacuum of the cosmos, and it is dominant. Our calculations show that all the stars and galaxies we can see, all the normal matter, makes up less than 1/3 of the universe. Dark matter makes up about 25%. The rest, roughly 70%, is this mysterious dark energy pushing the canvas of space apart at an ever-increasing rate. This brings us back to redshift. Redshift is not just a speed detector, it is also a time machine. Light does not travel instantly. It takes time for light to cross the universe. The Sun, for example, is 8 light minutes away. We see it as it was 8 minutes ago. The Andromeda Galaxy is 2.5 million light years away. We see it as it was 2.5 million years ago. When we look at a galaxy with a very high redshift, we are seeing light that has travelled for perhaps 10 or 12 billion years to reach us. We are seeing that galaxy as it was when the universe was young, looking far away as looking into the past. This is how astronomers confirmed the existence of dark energy. They didn't just look at the current expansion rate. They measured the redshifts and distances of supernovae at many different look-back times. When they did this, they saw the bend in the history of the universe. By looking at the most distant objects, the deep past, they saw that the expansion was actually slowing down just as gravity predicted. But when they looked at more recent objects closer to us in time, around 6 billion years ago, they saw the bend, where the expansion stopped slowing and started to speed up. This was the moment in cosmic history when the pulling force of gravity was finally overcome by the constant, relentless push of dark energy. Redshift, the simple stretching of light, it has become our clock. It tells us the story of our universe, a universe that started in a bang, was held back by gravity for billions of years, and is now being pushed apart into a faster and faster expansion by a ghostly energy we have yet to understand. If we had eyes that could see microwaves, the entire night sky would glow. It wouldn't be dark and empty, it would be filled with a faint uniform light coming from every direction. This light is the cosmic microwave background, or the CMB. It is the most important and revealing discovery in all of cosmology. This isn't light from stars or galaxies. It is something much older. It is the oldest light in the universe, a fossil left over from the dawn of time. The best way to think of it is as the baby picture of the universe. It's a snapshot of what the cosmos looked like when it was just 380,000 years old, as a mere infant compared to its current age of 13.8 billion years. To understand this light, we have to go back to the very beginning. For the first 380,000 years after the Big Bang, the universe was a completely different place. It was not dark and cold, it was incredibly hot and unimaginably dense. But it was also opaque. You wouldn't have been able to see anything. The universe was filled with a soup of particles called a plasma. It was so hot that atoms couldn't form. Tiny particles called electrons were not attached to protons. They just zipped around freely. This soup of charged particles was a perfect fog for light. Particles of light called photons couldn't travel more than a few inches before they slammed into a free electron and scattered in a random direction. The entire universe was like the inside of a star, or like being trapped in a blinding dense fog. But as the universe expanded, it cooled. This is the most important rule of the expanding cosmos: expansion causes cooling. After about 380,000 years, the universe reached a critical milestone. The temperature dropped to about 3,000 degrees, cool enough for the free-flying electrons to finally be captured by the protons. This process formed the first stable neutral atoms, mostly hydrogen. This event is called recombination. The moment this happened, the universe suddenly became transparent. With all the electrons now locked away inside atoms, the light particles, photons, were set free. The fog cleared. For the very first time, light could travel across the universe in straight lines, completely unobstructed. The light we now see as the cosmic microwave background is that very light released at that very moment. For 13.8 billion years, these first photons have been travelling through space, finally reaching our telescopes today. We didn't know this light existed until 1965. Two American astronomers, Arno Penzias and Robert Wilson, were using a large radio antenna to study the Milky Way. They kept picking up a persistent, annoying hiss in their equipment. It was like static on an old television. This noise was uniform, and it came from every single direction in the sky, day and night all year round. They checked everything. They even cleaned bird droppings off the antenna, thinking it might be the cause. It wasn't. What they had accidentally discovered was the echo of the Big Bang. It was the glow from the ancient hot universe. The reason it appears as a cold microwave hiss instead of hot visible light is because the universe has expanded tremendously since the light was released. As space itself stretches, it stretches the light waves travelling through it. This redshift has stretched the original hot light waves so much that they are now very long low-energy microwaves corresponding to a temperature of just 2.7 degrees above absolute zero. Penzias and Wilson saw a uniform glow, but the next step was to map this glow in detail. Several space telescopes were launched to do just this, including COBE Cosmic Background Explorer in the 90s, followed by WMAP, Wilkinson Microwave Anisotropy Probe, and most recently the Planck satellite. These missions gave us the baby picture. And when we looked closely, we found something incredible. The light is not perfectly uniform. It is covered in tiny microscopic ripples. There are spots that are slightly warmer and spots that are slightly cooler. These differences are minuscule, only about 1 part in 100,000. But these tiny ripples are the most important part of the picture. These are the seeds of all structure in the universe. Those slightly warmer and slightly denser spots were the seeds that gravity needed to get to work. Over hundreds of millions and billions of years, gravity pulled more and more matter, both regular matter and dark matter, into these slightly denser regions. These areas grew and grew, eventually collapsing to form the first stars, the first galaxies, and eventually the vast clusters of galaxies we see today. Every galaxy, every star, and every planet, including our own, grew from one of these tiny seeds, seen in the ancient light of the CMB. If the early universe had been perfectly smooth, none of this would exist. But this map does more than just show us the seeds of galaxies. It also tells us the age of the universe. We can figure this out by analysing the size of those ripples. Before the universe became transparent, that hot plasma fog was not quiet. It was ringing with sound waves. The two main forces at play, gravity trying to pull the plasma together, and radiation pressure, the push of light itself, trying to blast it apart, were in a cosmic battle. This struggle caused the entire plasma soup to vibrate or oscillate like a giant cosmic bell. When recombination happened and the light was set free, it essentially took a snapshot of these sound waves at that exact moment. The hot and cold spots in the CMB map are that frozen snapshot. Scientists analysed this map using a tool called the power spectrum. This is a way of measuring how many ripples there are of each different size. It is the cosmic equivalent of listening to a bell and identifying its fundamental note and all its overtones. The most common size of the hot and cold spots in the map tells us the fundamental note of the early universe. This is where the age comes from. We have a precise model of the universe called the Lambda Cold Dark Matter LCDM model. This model is like a recipe for the cosmos, with ingredients like regular matter, dark matter, and dark energy. We can use this model to predict what the sound of the baby universe should have been. We then fit this model to the actual data we see in the Planck map. We adjust the amounts of each ingredient and the age of the universe until the note predicted by the model perfectly matches the note we observe in the CMB's power spectrum. The result is a perfect middle match. The sound bits recorded in the CMB map only makes sense if the universe is 13.8 billion years old. This is our most precise and reliable measurement of the universe's age, and it comes directly from studying this fossil light, the first echo of our own beginning. We journey now from the expansion of the entire universe to the contents within it. If we want to know the age of the cosmos, one of the most direct ways is to find the oldest things in it and to measure their age. We cannot find a birth certificate for the universe, but we can find its oldest living residents. These ancient witnesses are the globular clusters, and they are one of the most beautiful and informative objects in the night sky. Imagine a vast spherical city of stars, not with thousands, but with hundreds of thousands or even millions of stars all crammed into a relatively small space. They are not like the loose young families of stars called open clusters found within the main disk of our galaxy. Instead, globular clusters are ancient and isolated, orbiting far above or below the galactic disk in a region called the halo. They are cosmic fossils, leftover relics from the very dawn of our galaxy's formation. The most important feature of a globular cluster for our purposes is that all the stars within it were born at the same time. They all condensed from the same enormous single cloud of gas and dust billions of years ago. This makes a globular cluster a perfect laboratory for studying stars. Because they all have the same birthday, any differences we see in them today, their brightness, their colour, their size, must be due to only one major difference: their initial mass. This single-age property allows astronomers to use them as extraordinary cosmic clocks. There are two primary methods we use to read these clocks. Method 1, the main sequence turn-off. To understand this method, we first need to look at the most important chart in all of astronomy, the Hertzsprung-Russell diagram, or the HR diagram for short. This is not a map of space, and it is a census of stars, a graph that plots a star's true brightness, its luminosity against its surface temperature, which we can tell by its colour. When astronomers plotted all the stars they could see on this graph, they found that about 90% of them, including our Sun, fell along a long, stable diagonal line. This line is called the main sequence. A star on the main sequence is in the stable adult phase of its life. During this time, it is doing one thing very, very well. It is fusing hydrogen atoms into helium atoms in its core. This fusion process releases a tremendous amount of energy which pushes outward and perfectly balances the inward crush of gravity. A star will spend the vast majority of its life on this main sequence. Now here is the critical rule of stellar lives: a star's mass determines its lifespan. A very massive star, say 20 times the mass of our Sun, has much more hydrogen fuel. You might think it would live longer, but it does not. Its immense mass creates crushing pressure and heat in its core, causing it to burn through its fuel at a shockingly fast rate. It's a cosmic gas guzzler. It lives a bright, brilliant, hot and short life, perhaps only 10 million years before exploding. A low-mass star like our Sun, or even smaller, has less fuel, but its core is under less pressure and is cooler. It sips its fuel slowly and efficiently like a fuel-efficient compact car. A star like our Sun lives for about 10 billion years. A star much smaller than our Sun could live for trillions of years. So let's apply this to our single-age globular cluster. When the cluster is first born, time zero, it is filled with stars of all masses, big, medium and small. On the HR diagram, this brand new cluster would have stars all along the entire main sequence, from the hot, bright, massive blue stars at the top left to the cool, dim, low-mass red stars at the bottom right. Now let's wind the clock forward 100 million years. What has happened? All the most massive gas guzzler stars have already burned through their fuel. They have died and left the main sequence. They may have exploded as supernovae or become red supergiants. The medium-mass stars like our Sun and the low-mass stars are just fine. They are still happily fusing hydrogen. Now let's wind the clock forward to 10 billion years. What do we see? Not only are the most massive stars gone, but the medium-mass stars with the same mass as our Sun, are also just now starting to run out of hydrogen fuel in their cores. They are beginning to swell into red giants, and they too are leaving the main sequence. The only stars still on the main sequence are the low-mass fuel-efficient stars, which will continue to burn for billions of years more. When we plot an HR diagram for a globular cluster today, we can see exactly where this is happening. We see a main sequence that is intact at the bottom low-mass stars, but is cut off at a certain point. This location is called the main sequence turn-off point. This turn-off point shows us the most massive stars that are still alive and on the main sequence. Every star above this point more massive has already died. The stars at this point are just now running out of fuel. By looking at the turn-off point, we can ask, what is the mass of a star that lives for exactly this long? If the turn-off point corresponds to stars that have a 10 billion year lifespan, then the cluster is 10 billion years old. If the turn-off point is even lower down the main sequence corresponding to stars that live for 12 billion years, then the cluster must be 12 billion years old. This turn-off method is the primary and most powerful tool we have for dating these ancient clusters. It is like looking at a large group of people who are all born on the same day and noting that the most elderly members are just now passing away from old age. Their lifespan tells you the age of the entire group. Method 2, the cooling of white dwarfs. There is another very clever method that acts as a check on our first one. This method looks not at the stars that are living, but at the stars that have died. When a star like our Sun A low to medium mass star finally runs out of all its fuel, it does not explode. After its red giant phase, it puffs away its outer atmosphere, creating a beautiful ghostly object called a planetary nebula. Left behind in the centre is the star's original core, a searingly hot, incredibly dense ball of carbon and oxygen called a white dwarf. A white dwarf is the stellar corpse. It is no longer generating any new heat through fusion. It is simply an ember. It is fantastically hot from its past life, and like a hot coal taken from a fire, it will now spend the rest of eternity doing only one thing, radiating its heat away into space and slowly cooling down. This cooling process is very, very slow, but it is also very, very predictable. A brand new white dwarf might have a surface temperature of 100,000 degrees. After billions of years, it will have cooled down, becoming dimmer and redder. After many billions of years, it will be very cool, very dim, and very difficult to see. Now think back to our ancient globular cluster. Over its long 11 or 12 billion year life, many of its medium mass stars have completed their lives and become white dwarfs. The cluster is filled with these cooling embers. Some of these white dwarfs are new. They only formed a billion years ago from a more recent star's death. But some of them are the original white dwarfs formed from the first stars in the cluster to die way back in its infancy. These original embers have been cooling for the entire age of the cluster. Astronomers using powerful tools like the Hubble Space Telescope can search the cluster for these white dwarfs. It's incredibly difficult work as they are trying to find the faintest, blackest coals in a blazing bonfire of a million other stars. But when they find them, they look for the dimmest and coldest white dwarfs in the entire population. These are the oldest ones. By measuring the temperature of these coolest embers, scientists can calculate how long they have been cooling. If the coolest white dwarfs we can find have been cooling for 12 billion years, then the cluster must be at least 12 billion years old. This provides a completely independent age measurement, a fantastic second opinion that confirms the age found from the main sequence turnoff. The final verdict, the cosmic age limit. So what do these methods tell us? When we apply these two techniques, the main sequence turnoff and white dwarf cooling, to the oldest globular clusters, we can find the answer comes back consistently. The oldest of these cosmic fossils are between 11 billion and 13 billion years old. This is a profound discovery. It gives us a hard physical boundary for the age of the universe. The logic is simple and undeniable. The universe cannot be younger than the oldest things living inside it. If you find a tree with 5,000 annual rings, you know with absolute certainty that the patch of land it grew on is at least 5,000 years old. The globular clusters are our oldest trees. Their 11 to 13 billion year age sets a lower limit or a floor for the age of the universe. This measurement was a spectacular triumph for cosmology. For many years there was a cosmological crisis where some measurements of the universe's expansion suggested the universe was younger than these clusters, a clear paradox. But as our measurements of both the expansion rate and the physics of stars improved, the numbers came into beautiful agreement. The age of the universe, as measured by its expansion, the Big Bang, is now confidently measured at about 13.8 billion years. The age of the oldest stars is about 13 billion years. This makes perfect sense. The universe had to be born first 13.8 billion years ago, and then after a few hundred million years for gas to cool and gravity to work, the very first fossil clusters could form around 13 billion years ago. The stars themselves, our most ancient witnesses, tell a story that is perfectly consistent with the story told by the expansion of all of space. For decades, cosmologists have been building a master theory of the universe. We call it the lambda-cold dark matter model, or LCDM for short. This model is our standard model of cosmology, much like the standard model of particle physics explains the subatomic world. It is simply put our official recipe for the cosmos. It has been incredibly successful explaining almost everything we observe, from the leftover heat of the Big Bang to the grand structure of galaxies. This recipe has three main ingredients. First, there is the normal matter that we can see and interact with. This is called baryonic matter, and it makes up everything you have ever touched: the stars, the planets, the gas clouds, and us. In the grand cosmic budget, this familiar matter is shockingly scarce, accounting for only about 5% of the total universe. The second ingredient is cold dark matter, CDM. This is the matter part of the recipe. We know it has gravity because we can see its effects. It bends light from distant objects, and most importantly, it acts as the invisible scaffolding for the universe. Without its immense gravitational pull, galaxies like our own Milky Way would never have had enough gravity to form. We call it dark because it does not interact with light. It is completely invisible. We call it cold because it moves slowly, allowing it to clump together and form the structures we see. This mysterious substance makes up about 27% of the universe. The third and largest ingredient is lambda L. This is the Greek symbol scientists use to represent dark energy or the cosmological constant. If cold dark matter is the engine pulling the universe together, lambda is the accelerator pushing it apart. It is a mysterious pressure embedded in the fabric of space-time itself, causing the expansion of the universe not just to continue but to speed up. This accelerating expansion was a Nobel Prize-winning discovery, and it is the dominant force in the cosmos today, making up roughly 68% of everything. This lambda cold dark matter model is the framework we use to understand our cosmic history. When we ask, how old is the universe? The answer, 13.8 billion years, does not come from a single measurement. It is the result of this model. Scientists measure the ingredients of the universe, how much dark, how much light, how much energy, by looking at data from the cosmic microwave background, CMB, the baby picture of the universe. They measure the current rate of expansion using supernovae exploding stars and the large-scale clustering of galaxies known as baryon acoustic oscillations, BAO. The 13.8 billion year age is the only age that allows all of these different independent observations to agree within the rules of the LCDM model. For years, this model has been the bedrock of cosmology, a stunning human achievement. But today that bedrock has a massive crack running through it. This problem, known as the Hubble tension, is the single biggest crisis in modern physics. The Hubble tension is a profound disagreement about one simple number. How fast is the universe expanding right now? This speed is called the Hubble constant. It is measured in a specific unit, kilometers per second per megaparsec. This unit sounds complicated, but the idea is simple. A megaparsec is just a huge unit of distance equal to about 3.26 million light years. The Hubble constant tells us how fast space itself is stretching. A value of 70 would mean that for every megaparsec a galaxy is away from us, it appears to be moving away at 70 kilometers per second faster. A galaxy 2 megaparsecs away moves at 40 kilometers per second, and so on. It is the fundamental speed of cosmic expansion. The problem is, we now have two different ways of measuring this speed, and they give two different answers. The first method is the early universe measurement. This method uses the lambda cold dark matter model as its instruction book. Scientists look at the baby picture of the universe, the cosmic microwave background, which was mapped with incredible precision by the Planck satellite. This map tells us the exact ingredients of the universe just 380,000 years after the Big Bang. Scientists then take these early ingredients, put them into the LCDM model, and run the simulation forward for 13.8 billion years. The model predicts what the expansion rate must be today. This prediction is incredibly precise. It gives a value of about 67 kilometers per second per megaparsec. The second method is the late universe measurement. This method does not rely on the LCDM model. It is a direct measurement of the universe as it is today. Scientists build a cosmic distance ladder. They measure the exact distance to pulsing stars called Cepheids, and then use those stars to find the exact distance to exploding stars type Ia supernovae in other galaxies. Because these supernovae are standard candles, they always explode with the same true brightness. We can tell how far away they are by how dim they appear. By measuring their distance and the speed at which they are moving away from us, we can directly calculate the Hubble constant. This late measurement, which has been refined for years, gives a different value. It gives us an answer of about 73 kilometers per second per megaparsec, 67 versus 73. This may not seem like a big difference, but to cosmologists it is a nightmare. Both measurements have been checked, double-checked and triple-checked. The teams are some of the best scientists in the world. Their measurements are now so precise that their error bars, the range in which they might be wrong, do not overlap at all. This means we are not looking at a simple error. We are looking at a fundamental contradiction. The universe predicted by our model of the Big Bang, the 67 value, is not the universe we observe today, the 73 value. This is the Hubble tension. It is the heart of the crisis in cosmology, and it means one of two things. Possibility one is that this is a crack. It means there is a hidden systematic error in one of the measurements. Maybe dust in space is fooling us. Maybe we do not understand the physics of Cepheid stars or supernovae as well as we thought. If this is the case, one side will eventually find their mistake, the tension will vanish, and the lambda cold dark matter model will be saved. Possibility two is far more exciting. It means this is not a crack in our measurement, but a door to new physics. It means our recipe for the universe, the lambda cold dark matter model that has guided us for decades, is wrong, or at least incomplete. The universe must include some new ingredient or new physical law that we have not yet discovered. Perhaps dark energy is not a constant lambda, but is changing over time. Perhaps there was a burst of early dark energy that gave the universe an extra push just after the Big Bang, changing the calculations. Perhaps dark matter is not as cold or simple as we believed. We do not know the answer. But the Hubble tension tells us that our standard model of the cosmos, for all its success, is not the final story. Something new is waiting to be found. We have travelled far on this journey, navigating the very mechanics of reality. We have followed the equations, traced the pathways of light from distant galaxies, and listened to the ancient echo of the universe's first moment. We have gathered the how, the physics, the chemistry, the data that builds the grand architecture of the cosmos. But standing here with all this knowledge in hand, we face a new, more personal horizon. We turn from the blueprint to the meaning. We move from how do we know to the essential human question, so what? This is the contemplative shore. It is the quiet place where the waves of data recede, leaving us to walk along the beach and reflect on the profound implications of what we have found. It is where science meets stillness, and where we must find our own place in the grand, silent story. The first and perhaps most jarring realization is the shattering of our own importance. For nearly all of the human history, we believed we were the center of it all. It was a comforting, intuitive thought. The sun rose and set for us. The stars wheeled overhead in a majestic performance for us. The earth was the steady, unmoving stage upon which the divine drama of our lives unfolded. This was a universe that knew our name, a cosmos built with us in mind. Then the great demotion began. It wasn't a single event, but a slow, steady erosion of our central place. We learned that our planet is not the center. It is a small rocky world, one of several that circles a star. This discovery was profoundly disturbing. It felt like being evicted from the heart of our own home, but the demotion did not stop there. We soon learned that our star, the Sun, is not special. It is an average medium-sized star burning yellow in a quiet suburban arm of a vast celestial city. This city, our Milky Way galaxy, holds perhaps 400 billion other stars, countless other potential suns, and then the final crushing blow to our ego, our galaxy, is not special either. It is one of perhaps 2 trillion other galaxies scattered through the observable universe. We are not the center of the world, we are not the center of the solar system, we are not the center of the galaxy, we are not the center of the universe. There is no center, or if you prefer, everywhere is the center. This is the great cosmic humility. The universe is not hostile, but it is deeply, profoundly indifferent. It was not made for us. It does not revolve around our hopes, our fears, or our desires. This realization can feel cold. It can feel like loneliness, a sense of being a tiny, accidental speck lost in an ocean of uncaring infinity. But there is another way to see it. This humility is also a liberation. When we accept that the universe was not made for us, we are free to discover the more profound truth we are made from it. We are not its masters, but we are its children. We are not the reason for the cosmos, but we are a result of it. This removes the burden of cosmic self-importance and replaces it with a simple, quiet sense of belonging. We are just as much a part of this story as a distant quasar or a ring of interstellar dust. We are a momentary, beautiful pattern that has arisen from the same fundamental laws that guide the orbits of planets and the burning of stars. We are not special, and in that ordinariness we find an authentic, humble connection to everything. That connection is not just poetic, it is literal. It is written into our very biology. When we look at our hands, we are looking at materials forged in the hearts of long-dead stars. This is the second great contemplation. We are stardust. Let us rewind the clock. In the first few minutes after the Big Bang, the universe was a screamingly hot, dense forge, but it was a simple one. It created the lightest ingredients, an ocean of hydrogen, and a good amount of helium. For millions of years, that was the entire universe, a thin, invisible, and frankly boring gas. You are not made of just hydrogen and helium. Look at yourself. You are built from carbon, the backbone of all life. You breathe with oxygen. Your thoughts are powered by the electrical signals of sodium and potassium. Your blood carries oxygen using iron. Your bones are structured with calcium. Where did all this stuff come from? It came from the stars. Gravity, the universe's great sculptor, pulled that primordial hydrogen gas into massive clouds. These clouds collapsed, and in their cores the pressure and heat became so intense that a new fire was lit. The first stars were born. Inside these stellar furnaces, a new magic began: nuclear fusion. Hydrogen atoms were crushed together to make helium. Then helium atoms were crushed together to make carbon. Carbon and helium made oxygen. In the cores of massive stars, the assembly line continued creating heavier and heavier elements. But these precious heavy elements were trapped inside the stars that made them. For them to get out, for them to become available to build worlds and people, the stars had to die. And they had to die violently. When a truly massive star exhausts its fuel, it collapses and then explodes in the most powerful event the universe ever creates: a supernova. For a few weeks, this single exploding star can outshine its entire home galaxy. In that final catastrophic blast, all the elements we know, the iron, the calcium, the gold, the uranium, are forged and hurled out into space at incredible speeds. This debris, this dust, drifts through the cosmos for billions of years, mixing with other clouds of gas. Eventually, gravity pulls this enriched dust together again. It forms a new generation of stars, and circling them, planets. Our solar system is one such product. Our Earth is a third-generation world, a planet built from the ashes of stars that lived and died long before our sun was ever born. Every single heavy atom in your body, from the iron in your blood to the carbon in your brain to the calcium in your bones, was created in the heart of a star that exploded billions of years ago. You are not just living in the universe, you are the universe. We are the cosmos recycling itself. We are, in the most literal sense, the ashes of dead stars reassembled for a brief time and given the astonishing gift of life. When you look up at the night sky, you are not an outsider looking in. You are looking at the furnace that forged you. We are stardust that has awakened. This awakening is part of the third great theme. The universe is a story of rising complexity. The history of 13.8 billion years is not just a random series of events, it is a ladder. It is a story of simple things following simple rules automatically and elegantly, arranging themselves into more and more complex and interesting structures. Think of the very beginning. The universe was a hot, uniform, featureless soup of energy and particles. It was the definition of simplicity. There were no things, there were no structures, no planets, no atoms, no life. Then the universe cooled. The simple particles locked together to form the first atoms, hydrogen and helium. This was the first step up the ladder of complexity. Gravity took over. This simple, persistent force pulled those atoms together. The smooth, uniform gas broke into massive filaments, then into clouds, then into the first stars. Suddenly, the universe was not smooth, it was lumpy. It had structure. It had places. This was the next step. Those stars, as we've seen, became factories. They took simple atoms and fused them into complex atoms. The periodic table was born. The chemical richness of the universe emerged from the simplicity of hydrogen. Another step up. Those stars died, scattering their complex atoms into space. These atoms, now rich with new possibilities, began to interact. Chemistry was born. Atoms linked up to form molecules. Simple molecules linked up to form complex chains of carbon. On at least one small wet planet, these complex molecules began to cooperate. They formed membranes, they captured energy, and critically, they began to make copies of themselves. Life began. This was a new revolutionary level of organization. Matter was no longer just reacting to the laws of physics, it was using the laws of physics. Life captures energy, it fights against disorder, it adapts and it remembers. The ladder of complexity continued to build. Single-celled life became multi-celled life. Cells specialized, forming tissues and organs. Creatures developed nervous systems to navigate their world. Brains evolved, becoming ever more complex processors of information. All of this happened without an external plan. It was not designed, it was emergent. The simple fundamental laws of physics applied blindly over billions of years are a recipe for self-organization. The universe, it seems, has a built-in tendency to build interesting things. It is a complexity machine. From a simple hot plasma, the cosmos has spontaneously generated galaxies, stars, planets, chemistry, and life. We are not a miracle. We are an inevitability of a universe that is hardwired to create structure. This brings us to the final, most profound contemplation. In all this vastness on this one small planet, the process of self-organization reached a threshold unlike any other. The universe created a form of matter that could do something new. It could look back at itself. This is the gift of consciousness. For 13.8 billion years, the universe was a magnificent silent show. Galaxies collided, stars were born, supernovae exploded, a cosmic drama of immense power and beauty. But with no one to watch it, The universe was, but it did not know that it was. And then on this little speck of awakened stardust, the complex self-organizing brain crossed a final frontier. It became aware. We are the universe's way of knowing itself. This is a staggering thought. That collection of atoms you call you-atoms, forged in stars organized by the laws of physics, is the part of the cosmos that can think, feel wonder, and understand. When you look up at the stars, you're not just a person looking at the sky. You are the universe itself turned into a sensory organ looking back at its own fiery origins. When you study mathematics, you are the universe discovering the elegance of its own laws. When you write a poem about the beauty of a sunset, you are the universe finding a language to describe its own majesty. When you ask, where did I come from, and why are we here? That is the universe becoming self-aware, grappling with the mystery of its own existence. We are not separate from the cosmos. We are its thinking, feeling edge. We are the custodians of meaning. In a universe that is largely cold, dark, and unthinking, we are a small, warm spark of awareness. We are the universe's local office for consciousness. This reframes our place completely. We may be small, we may be temporary, but we are not insignificant. We are the part of the story that gets to understand the story. To stand on this contemplative shore is to finally find peace. We accept our cosmic humility. We are not the center of it all. We embrace our deep connection. We are made of the stuff of stars. We marvel at the process. We are the product of an unfolding, self-organizing universe. And we cherish our unique role. We are the mind of the cosmos, the consciousness that allows it to be known. We are infinitesimally small, and yet we are immeasurably profound. We are a brief flicker of light, but in that flicker we contain the entire history of time. And in that recognition there is a deep quiet and abiding sense of peace. Our long journey through the cosmos is coming to a close. We have travelled across vast stretches of space and time, not as physical astronauts but as curious minds. And on this journey we have found that we are not observers looking at a dead and silent stage. Instead, we have discovered that we are living within a universe that remembers. It is a universe that keeps a meticulous record, a grand archive of its own past, leaving clues and traces for anyone patient enough to read them. These traces are not hidden away, they are everywhere. They are in the light that travels from a star a million light years away, carrying with it a snapshot of a past that is long gone. That photon, that particle of light, is a memory. When it finally reaches our eye, we are looking at a ghost, a perfect record of what was. The universe in its very laws ensures that the past is never truly erased. It is simply carried forward, rippling outward like the wake of a boat. We see this memory in the elements that make up our world. The iron in your blood, the calcium in your bones, the oxygen you are breathing in this very moment. These were not present at the beginning. They are the legacy of stars that lived and aged and died in tremendous explosions billions of years ago. Those stars are gone, but their story is not. Their life's work is written into the periodic table, and that story continues inside of you. You are quite literally the living memory of a stellar past. You are the universe's way of recycling its own history. This is the great unfolding story that everything points to. It did not begin with the complexity we see today. It began with simplicity. It began with the first atoms, tiny drifting clouds of hydrogen and helium, the simplest elements of all. In the beginning, the universe was dark, a vast and quiet fog. But it was not static. Gravity, the quiet and patient hand of the cosmos, began to pull these simple atoms together. It gathered them into massive clouds, then crushed them under their own weight, igniting the first stars. In the fiery hearts of those first stars, the universe began to write its next chapter. It learned to forge heavier elements, a kind of cosmic alchemy. When those stars died, they scattered their newly made creations into the void, seeding the next generation. From these enriched clouds, new stars and new planets formed. And on at least one of these planets, our own, the story continued. The universe's memory, encoded in chemistry, began to organize itself. Those same simple atoms forged in ancient stars assembled themselves into complex molecules. Those molecules learned to copy themselves. Life began. From that first spark to the ancient sprawling galaxies we can now see with our telescopes, everything is part of one continuous unbroken narrative. You are the most recent paragraph in a story that began long before our sun was born. You are the direct descendant of those first atoms. This is not a philosophy, it is a physical fact. The sheer scale of this story is almost impossible to hold in our minds. We speak of 13.8 billion years of cosmic time. This number is so large that it becomes meaningless, but the universe does not forget a single second of it. That entire history, all 13.8 billion years of it, is written in the silence that stretches between the stars. We often think of space as empty. We call it a void. But it is not empty at all. It is full of the past. It is full of the faint stretched out light from the very first galaxies. It is filled with the oldest message of all the cosmic microwave background. This is the faint leftover warmth from the Big Bang itself, a gentle, pervasive glow that fills every corner of the sky. It is the universe's baby picture, the echo of its own birth, still whispering to us after all this time. The silence of space is not an absence, it is a library. As our exploration ends and as you prepare for rest, let this understanding settle over you like a comforting blanket. The universe is not a cold, random and meaningless place. It is a single unified unfolding event. It is a story that builds upon itself, a system that remembers its own past to create its future. And the most beautiful part of this realization is that you are not separate from it. You are a part of this cosmic memory. The same laws that shape the orbits of distant galaxies are the laws that govern the firing of neurons in your brain. The same atoms that burn in the heart of the sun are the atoms that allow you to feel, to think, and to wonder. You're not just a witness to this grand story, you are an active participant. You are the universe becoming aware of itself. So as you close your eyes, let go of the day, feel the gentle pull of gravity holding you securely. Listen to the quiet rhythm of your own breathing, a rhythm shared by all living things on this planet, all of you part of the same ancient family tree. There is no need to feel small in the face of this vastness. You are as much a part of the cosmos as the brightest star. The universe remembers its long, slow journey from simple gas to conscious life, and that memory lives within you. You are a precious and complex piece of a story 13.8 billion years in the making. Let this knowledge bring you peace. Let it be an anchor in the quiet of the night. You are home, you are made of stardust, you are resting in the arms of a universe that remembers every step of the journey that led to you. Now with this new understanding, you can drift into sleep held safe within the greatest story ever told.